So I'm going to give an outlook talk about quantum computing, a little bit about the basic principle, about the present architectures and future possibilities, and also I will relate it a little bit to GPUs in the end. So actually, I start with something seemingly completely different. As we all know, the most popular public key crypto system is the RSA system, named after these three gentlemen. And it uses actually an observation that multiplying two integers is very easy, let's say multiplying two primes. However, if you have a huge integer and you want to find the prime factors, that's a very hard task. For example, I gave here a number which has 232 decimal digits, or in bits it would be 768. and of course it's pretty hard to find. I gave actually the prime factors for these. I will talk a little bit about that, who made that. But to multiply, everybody in the room could just run that on the computer. It's like in a few seconds. And actually that number came from something called the RSA factoring challenge, where they give out huge products of two prime numbers, and they give some prizes if somebody can factor, just to test how well this assumption about that factoring huge integers is good enough. And actually the number I showed you previously was the largest such numbers that could be broken and taken into prime factors, broken into prime factors. But for example, a similarly large number with 230 decimal digits, which I gave you here, hasn't been, they couldn't find prime factors. And for example, maybe you cannot see, but for example, a number containing 2024 bits, where they gave $100,000 for factoring, nobody was able to do it. So it seems as a pretty hard task, and it's of course good for these crypto systems, but maybe somebody would like to do it. And this crypto system was built in 1978, and actually around the same time in the physics community a question arose by Richard Feynman, who asked the following question. I mean, in physics we want to describe, for example, systems like, let's say, quantum dipole moments of electrons or of atoms in some materials. And even for the simplest quantum dipole moment, if you take 100 atoms, which would be a really small system, to describe that, actually you would need to describe a 2 to the 100 times 2 to the 100 matrix. And each matrix element would be some complex number that you have to somehow truncate. And actually, there were no computers at that time that could handle that. But he went on and saying that actually no other computer or usual computer built on usual ideas can simulate that in the future, because you would need actually more storage than the number of atoms that are in the universe. So from that question, what to do, he gave a proposal. He said that trying to find a computer simulation of physics should be an excellent program, but he says that he's not happy with the classical theory of computing because that doesn't work for simulating physics. But what if we would simulate quantum physics with quantum physical other devices? And that was basically the first proposal for a sort of quantum simulator or quantum computer. And that became a very fruitful proposal. Just a few years after that, actually, people started to find quantum algorithms also for problems outside physics. One was the Deutsch algorithm in '85, which I will talk about. The other was the Shor algorithm, which actually showed that if you would have a fully functioning quantum computer, it would be easy to find out the factors of huge numbers. So you could break the RSA code. And then there was also other algorithms, for example, the Grover algorithm, 2 years later than the Shor algorithm, that showed that one could get also an advantage on searching on unstructured databases. Okay? And I mean, of course, recently, again, there is a huge buzz around quantum computing. I mean, everybody talks about this, from EU officials to the Canadian Prime Minister who just visited the Institute of Quantum Computing exactly in Canada, in Waterloo. Also, a recent Nobel Prize was given to related research to Harosh and Weinland. And many of my, for example, friends, fellow physicists, they get job in multinational companies, for example, at Google or IBM. Actually, I show one of those guys there. And then there are strategies in the US and in the EU to enhance the quantum computing research. And of course, even in GPU days, there are talks about this. So there should be, there is huge interest in this, apparently. Okay, so as I told you, for example, I mean, many of the big companies, I will talk about Google and then later about IBM, have their own quantum computing departments. Even actually, they have the position of a quantum engineer. I show one of my friends who is a quantum software engineer. Then there are the quantum electronic engineers and so on. But, and then there is a lot of startups. This you can, for example, there is a full Wikipedia page on startups that only work on quantum computing, and actually this is just the start of that page where they list these companies. But actually this was not, people were not that optimistic about quantum computing so long ago. For example, Serge Harosh, who just, I told you, got the Nobel Prize to research related to quantum computing, wrote an article about quantum computing dream or nightmare, where he said that actually it's fruitless to concentrate on quantum computing in the near term. And actually, the other Nobel Prize winner, Weinland, reacted to that with this another paper, Future of Quantum Computing, proves to be debatable, where he said that maybe Harosh was too harsh, but still he was also very negative. Okay, but now people are more positive. Who knows what the truth is? I mean, we all know that there are these emerging technology hype cycles when sometimes we think that there could be many actually of cycles, that some technology is evolving, sometimes there is a downturn. But there is something which is, of course, pressing for the need of quantum computation, and that's, I think, more than only the hype cycle that keeps these big companies from investing into quantum computing. And it's, of course, Moore's law, because, I mean, Moore's law can be formulated for in many ways about how, for example, for the same amount of money, how much more computational power you can get, or how much in one small area, how many processors you can put into. But of course, I mean, when you go down and down to atomic scales, quantum effects become more and more dominant. And of course, right now, what people do in these usual computing companies is that they actually try to decrease these quantum effects as something unwanted. And after a while, there should be a change where we want to use this. Okay, so now let me give of the rest of the talk a few outline. I will talk a little bit, I cannot stand, about the principles of quantum computing, then talk about two architecture types, two main ones that are currently used. One is the gate model, the other is the adiabatic quantum computation. And then also I will try to show what we can do with quantum computers. I mean, I mentioned one thing, factoring numbers. Unfortunately, actually, there are not too many well-defined classical tasks that you can do with it, but still some people have some ideas what to do. And then I look on some future perspectives. So basically, the basic unit in quantum computing is the qubit. I mean, in many cases, when we describe some system with quantum mechanics, the system can have only two states, and that's the simplest case. This goes, for example, for for the magnetic dipole moment of an electron. So you can imagine that as a small magnetic vector that can point upwards or downwards. Or the polarization of light, which can be like vertically or horizontally. Or the flux or the direction of current in superconducting rings is one of those. So that in the superconducting ring, the current goes in one direction or in the other. Okay, I mean, there are two states. What's special? Well, the special about this in quantum mechanics is that you don't, if you have such a two-state system described by quantum mechanics, you can actually provide a plethora of states, namely, which you can describe somehow as a formal linear combination of the two states. I mean, here, let's say 0 is one of the states. Let's say that the magnetic dipole moment or the spin of the electron points upwards, and 1 is that it points downwards. And then you can have any state of the form where you multiply it with a complex number, or you can imagine as a real number, because quantum computing actually also works. If you would imagine real numbers, a plus b1, okay? And here, the square of a gives you the probability that we find the system, if we measure that, in the state 0, so that it points upwards, and b squared provides the probability that we find it in a state that points downwards. And of course, since these are probabilities, h squared and b squared, they have to add up to 1. So that's the basic unit of quantum information, a qubit, and that's the general state of a qubit. Okay, and of course, maybe you have heard for sure about the most famous qubit, which is the Schrödinger's cat qubit, where the two states should be that the cat is dead or alive. And we think that if this could be described in a quantum mechanical coherent way, we could even superpose that. But then one could ask, what's the difference if we would, for example, say that I put it here square root of 1/2 a cat that is alive plus 1 divided by square root of 2 that it's dead. So the probability is basically 1/2 that it's alive and 1/2 is dead. But what if I would put a -1, which I'm allowed to? Would it make any difference? And actually it would, because this is the main thing. Quantum mechanics is not only about these probabilities, but also that these probabilities can be sort of coherently superposed. Okay, so basically I will come back to that question, but let me tell you so now we have the states, the basic states of quantum computing. Now we also want to have the operations. The operations are basically that we map a generic state, let's say, or the state 0, to another qubit state, which I denote by A0 plus B1. So we knew that these were the most general form of a qubit. And we map the state 1 into another one, the C0 plus D, the state 1. And from these two, if we know these two rules, then all the allowed operations are such that we can extend these rules in a linear fashion like that. And get for any generic state, which would be a linear combination of 0 and 1, we would get that it has to be mapped to that state. Okay, so we can gather these numbers describing this V operation in the matrix, and actually it will be a unitary matrix, and these are the basic operations in the quantum computing. And of course, I mean, talk about 1 qubit, but you can also talk about 2 qubits or 3 qubits or n qubits. And then what you have for the example, in the 2 qubit case, the most general state is of the form that we have with some probability 0, 0, with some 0, 1, with another one 1, 0, and then 1, 1. And then we can again have certain linear operators on it that are the allowed operations. Okay, so coming back to the Schrödinger cat example, according to one of the founders of quantum computing, Reinhard Werner, the surprise in Schrödinger's thought experiment is not that the cat can be with 50 probability alive and 50 is dead. Rather, the fact that there is a resurrection operator. What do I mean by that? Okay. Well, this operator is called the Hadamard gate, which acts on the zero state in the following way, that it gives it equal probability 0 and 1, and on the 1 state also equal probability 0 and 1, but with a minus sign here, because you know that only the the square of the number in front of the state gives you the probability. And if we look how such a operator acts on a Schrodinger cat state, so for example, it's that it's alive plus it's dead age, then it turns out that if you do the math, then that this age will map this strange alive and dead state into that the cat is alive. Only quantum physicists use 0 for alive, by the way. So this is the famous resurrection operator. But if the cat would have been in the other state, this alternative cat state that I told you, with the minus here, then it would actually map it directly to 1, so that to that cat. Okay, so let's use this operator. Actually, as I mentioned, after Feynman, 3 years after Feynman's thought experiment, British physicist David Deutsch posed the following problem. First, in classical computational theory, suppose that we have a Boolean function f, which maps a bit to another bit. So if you give 0, it can map 0 to 0, or 0 to 1, and 1, it can map 0 to 1. So if you want to decide whether f is a constant function or not, namely that it maps 0 to 0 and 1 to 0 also, or maybe it's not like constant like that, how many times do you have to query f? How many times do you have to ask f for? How many tries do you have to use? Obviously 2. You have to check when it's 0, and then you have to check when it's 1, what f gives. But then he made the following thought experiment. Suppose now that we do we take this function. I mean, this function can be, of course, because the fair comparison actually with quantum computing is actually the reversible computation. So the basic thing is that we can imagine the machine generating this function in the following way, that we give you an input x, then we get back x, and then we get also back fx, or if we have a y here, y plus fx. And that's how we can read out fx. If we would have the same thing with the quantum device, then it would mean again that we could just plug in here the x, the bit or the qubit that we want, and then we would get out the answer here. He put actually y to be 1, but that's just a technical remark. And then he said that, okay, but suppose now that instead of plugging in 0 into the input, testing x, we would plug in an equal superposition of 0 and 1, which actually we can get applying this resurrection gate, the Hadamard gate. Okay, then the output of the machine, if we follow the rules that I wrote up, will actually contain f0 and f1, f0 and f1. So in some way, it already contains the answer, whether it's constant or not, because it contains both f1 and f0, this output. But then we have to measure this. And how can we obtain the answer from that? And then he made a very nice derivation that if we put, again, a Hadamard gate here and make a measurement here, then on the first qubit, I mean, you can do the math. If the function f was a constant function, then with 100% probability, the state would be 0. If f would be not constant, then with 100 probability, if we would measure here, it would be 1. So just with one query, we just put in a linear combination of 0, and then make a measurement. We will get out the answer whether the function was constant or not. Okay, I mean, it doesn't sound too exciting, but with his student, who's actually of Hungarian origin, Józsa or Józsa, Deutsch actually implemented this also for any Boolean function with any variables. And he showed that using this Hadamard gate, these resurrection gates, and this UF function, actually only one trial, so only one query was enough to show whether U was a constant function or not. So this is actually, this thing is exactly the thing about the quantum parallelism, or the naive quantum parallelism, because what does these Hadamard gate implement? Well, if you put in 0, 0, zeros here, and then number of Hadamards, then actually what you get is an equal superposition of all possible of all possible bit strings. So you get the 000 bit string, you get the 1000, the 01000, and also all until 111. You get all of them with equal superposition. So if you would have a quantum processor that would implement this fx function, then you would somehow get out all the answers immediately. Why do I call it naive, this picture? It's a naive picture because even though you have the answers here, it's in a state and you have to measure it, and then maybe you only get this answer. So you have to do something else to refocus it and give you the answer. And there are only a few cases when we can do it. One is this algorithm by Deutsch. The other is by Shor, who actually used exactly such a refocusing method to show that you can factor numbers with only a polynomial number of operations. Of course, experimentally we only can factor numbers of let's say of the order of 56,000, which is very small compared to what we could factor in the RSA challenge, obviously, as we talked about. But okay, who knows? I mean, in the long run, if there would be a very fully functioning quantum computing, then it would be much faster than classical computers. Okay, this was one of the models, the so-called gate model, where we apply these linear operators and measurements and get out the answer like that. The other model is the so-called adiabatic quantum computation, where basically you encode the problem into the state of a system. And you know that, for example, if you have there is this famous satisfiability problem, and that could be actually mapped into a problem of finding the ground state of some physical Hamiltonian. So I don't have too much time, but basically the Adiabatic theorem says that that if you start from a state and you make the time evolution governing the system, the Hamiltonian, you change it a little bit with time, then the system stays in its ground state, and somehow with that method you can obtain the ground state of any Hamiltonians, and that would actually imply that you would be able to solve the three-set problem, okay, which would be an NP-complete problem. And actually, in the first paper about this, they tried to convince people that now they can solve NP problems with quantum computers, but this is not true because there is a condition that somehow the gap of the system, which is the eigenvalues of this Hamiltonian, don't close, and actually in the end they close. And one can show that the adiabatic model and the gate model are computationally equivalent. Okay, so let me just talk a little bit about the two hardwares. I have little time. One is the D-Wave, which actually somebody is going to talk about tomorrow, which is exactly implementing this adiabatic evolution, so slowly changing the Hamiltonian and then solving basically a three-set problem. And the other one is a gate model, which actually you can access. Actually, I use it a lot. This is IBM put, let's say, online a cloud quantum computer, actually many of them, some 5-qubit and some 16-qubit quantum computers. You can either use Python to program it, or for the 5-qubit one, you can just put gates in a graphical interface. And for example, this is how it actually looked like, and I was supervising or partially supervising. I mean, the main supervisor was András Pályi, a very talented student, Ákos Budai, who made a BSc thesis analyzing this quantum computer and, for example, showed how much noise there is there. So it's freely accessible to anybody. They also have other machines which are only accessible to certain partners of IBM, but also can be accessed online. And now we could ask, what can a quantum computer do? This goes into the computational complexity theory. I just showed this computational complexity plot to show you that, of course, this is a very complicated theory. But the easiest part of this is the so-called NP problems, which are problems that have a parameter n, which somehow measures the size of the system. And the NP means non-deterministic polynomial, that actually, if you are given the answer, somehow you can you can get the answer in you can check the answer in polynomial time. However, still, if you can check the answer in polynomial time, it doesn't mean that you can get the answer in polynomial time. If you can get, then you are in P, and then there is also the NP complete problems, like the traveling salesman problem or the tree set problem, which are such that if you could solve these in polynomial time, then you could solve any of those. And nobody believes now that quantum computing can actually solve these NP-complete problems. They only believe that they can solve more than P. For example, factoring is probably not in P, but just a little bit more than P. And I took this, I mean, this is actually a very debatable future perspective from Morgan Stanley research, who made research what quantum computers can be used for. I mean, of course, simulating quantum mechanics and quantum chemistry is one of the things, then factoring. Then they also claim that many machine learning tasks, this is also a big topic, can be advanced by quantum computers, which makes sense because it's mostly linear algebra, and you can see that that's somehow the good thing. So this is what they believe in. And just to close off, because I also show that there is actually a lot of things going on using GPUs. But actually, mostly what's going on is that GPUs are, of course, very fast and very big, and now we are dealing with systems of 20 qubits, 40 qubits, and after a while, of course, classical computers cannot benchmark the quantum computer. I mean, that's the point, that quantum computer has a much larger state space, and it's much has operations that the classical computer cannot simulate. But at the moment, actually, GPUs here, I just took a very recent paper, but there are like zillions of papers like that. They use GPUs to benchmark quantum computers. I mean, existing quantum computers, and they run the same program, just with classical methods. Okay, so thank you very much for.
Sorry, maybe I misunderstood, but
yes.
You use these clouds or quantum machines available,
yes.
But besides testing, has been real problems been solved using this?
I mean, no, because like the biggest one that you can access is, for example, you or I could access is a 16-qubit one, and of course, everything in a 16-qubit quantum computing you can simulate with a classical computer. So of course, people have run the Shor algorithm and so on, but they can do it with classical computers as well. But let me tell you something. Like previously, people said that 40 qubit, when we have a 40 qubit quantum computer, then we will reach the quantum supremacy when a classical computer cannot anymore simulate that efficiently, or actually in our lifetime, let's say. But this is also turns out not to be true. So Microsoft built this Q Sharp, okay? With them, I mean, it's also freely available, but they have a deliberate bug in the program that you can only run it for 23 qubits, but they can run it for 40, 41, 42 qubits. So now people say that maybe 60 qubits is the limit that you should reach. Then you cannot. Then you can do something interesting that you cannot do with classical computers. But with here, you can only just experiment and see what's going on. But you could have run those algorithms on classical computers. I'm not sure I answered your question.
Yeah. Next.
So can you tell us a little about error correction and how many additional qubits? When it might become feasible to actually use this?
That's actually a very nice or a very nasty question, actually, because first of all, I can tell you that I mentioned two architectures. One architecture is the adiabatic quantum computing, and the other is the gate model. For the adiabatic quantum computing, nobody believes that, nobody has shown in theory, and nobody believes that there exists actually a feasible, or actually error correction. It's a little bit related to the fact that there is no error correction for full-scale analog computers, actually. Okay, there is only an error correction if you digitalize it. For the gate model, actually, you have error correction, which is actually a huge theoretical step. I mean, this was done in the 90s. You can make it. But unfortunately, the numbers are very, very bad. So we have to then distinguish between the qubits, the physical qubits, and the logical qubits after in the error correction part. And then depending on how big, let's say, error we assume, if we assume, let's say, I mean, first of all, we have to assume like small errors, but small but fixed errors on each qubit. And then, of course, the numbers are very bad. So if you want to have error correction, then, of course, the number of physical qubits have to be huge, still growing only polynomially, but huge, corresponding to how many logical qubits you have to have. For example, typically, one would say that one logical qubit, for one logical qubit, you should have thousands of physical qubits. So unfortunately, if you want to have that type of real precise computing, this will not be possible in the future. But one of the main guys in the field wrote actually about these noisy quantum computers. I mean, you have to live with, maybe the road now is to just assume that there are some errors that you don't correct, but maybe they don't do too much, and you work with that. But I agree, error correction is necessary, and at the moment we are not even near close to do that.
Okay, one short question.
Maybe I missed the point. You mentioned the possibilities how to implement in a physical reality
yes.
qubit. Do you know what exactly is working inside the IBM or the Google machine? What's the physical principle they are working with?
So you remember maybe this plot? I didn't want to talk about the implementational issues, but I showed you the plot about the different qubits, okay? And basically, they have so-called superconducting qubits. Superconducting qubits can also be a different one, and one is how much somehow magnetic flux. It's also quantized in a superconducting ring, how much, whether the magnetic flux is pointing upwards or downwards, or whether you have a current which is in going left or right. And this is the qubit that they use in both in the IBM machine and in the Google machine, and also in D-Wave actually. All of them uses this qubit, but not these three companies uses that qubit, but there are also other companies that use, for example, the magnetic dipole moment of nuclei, okay, NMR, and so on. So there are those also.
Okay, so let's thank Zoltán again.
Thank you very much.
And,